Good morning, everyone. Well, what is it they're saying now? Welcome to springtime. Oh, got a little bit of rain. The pollen's back. So if you were enjoying being able to breathe freely, now we have to little bit of issue with the pollen. But I've lived here long enough that I'm finally good with it. I don't take the allergy medicine anymore. I don't take the Advil for headaches and things. I just finally said I'm done with all of this. And I take my vitamins and drink my water. So if I get the sniffles or a little raspy, I just rather do it that way. So that was my kind of like my resolution several years ago, and I think it's working out okay. But again, I love the weather in Houston, the temperate climate. I'm used to it, and I'm all good with it. So I hope you're doing well today. Um, what we want to do today is finish up a couple of topics with the inverse trig functions, and then move into some topics in chapter 6, where we talk about arc length, sector area, degree measure, and circular motion. So these are topics that I told you last class that you'll think this is more like a physics class, but I want to reiterate that with the inverse trig functions, you remember I went through all of them. So the way to have understanding and confidence with inverse trig is that you know the parent functions, and that means you know the range and domain, you know the inverse equations, which again, the range and domain give you the restrictions on the input, and you know how the inverse trig function operates on the negative argument, the additive inverse of x. That's imperative, because without that, we're not working with a valid function. So we define it a certain way, but then we have to always respect that definition. And that is a little bit more complicated than what we've been doing. So what I wanted to do first is kind of hit home with that idea. So again, I don't want you to look at these problems and say, oh, well, I'm just going to keep my fingers crossed and guess. No, that's not required. It's just like thinking about the unit circle going backwards, looking at the reverse path. Now, what I told you that I wanted to do at our last lecture, ladies and gentlemen, was to go over a couple of justifications or proofs for some of the identities that I spoke of. And so now, of course, we work with the unit circle, we work with our definitions. And then, of course, as we get to chapter 6, we may be able to look at things a little bit differently in terms of right triangles. So as we begin to mesh the two types of interpretations of the trigonometry, you'll see that certain things are illuminated, and then other things we see just kind of come into the picture that we didn't have with the unit circle. So as you work through mathematics, you're going to see a juxtaposition of different interpretations that don't even appear to be equivalent. But as you study them more, you see the equivalence. And so, of course, we experience that as we study math, and you will continue to see that in your careers. So the first thing that I wanted to do is look at a lemma. I'll just call it that for now. Remember, at the very end of the class, I said something about complementary angles. So this had the illusion of that. So if we took the inverse sine of x, and this worked for 3 pairs of functions, but we'll just look at this one, and we added that to the inverse cosine of x, we get the pi over 2. Now you remember, and this is a stretch to what we're doing today, but we will just be able to validate very simply that pi over 2 is equivalent to 90 degrees. So when you did your geometry, those of you earlier in your high school careers or back in high school, if you're already out of high school, you talked about angles being complementary when their sums were 90 degrees. And so, or supplementary when their sums were 180 degrees. So that was a context that you learned quite well in high school. So when we look at this, we have to think again, how do we approach this and respect the ranges and domains of the inverse sine and the inverse cosine? Well, first, what I want to do is make the following acknowledgement. So I'm going to say y here, and we're going to go about some justification. Now, one thing that's important here is that we just note, and I'm just going to do a little aside here, observe. We know at least up here, I'm just going to do a little sidebar, just saying about something about these particular functions. X must be in the domain of the inverse cosine and the inverse sine. So we know X lives between -1 and 1. So that's a given from what we did last class. As we restricted the domain, we get the output again going in the reverse direction. And then the inverse sine, where does it live? It lives between -pi/2 and pi/2. That's our definition. And then the inverse cosine lives between 0 and pi. So lots of times when we have to work with sine, and inverse cosine, we have to work a little bit harder because their ranges don't complement each other in a way that helps us out. We like them to be pretty much the same, and they're not. So what we're going to do is think about how we define sine and cosine from the unit circle. So here's what I'm going to start out doing. I'm going to define a variable theta. And your WebAssign goes through an example like this, and I'm basing my argument on the similar argument that WebAssign presents to you. It's a very good one. They don't go into as much detail, but it's certainly a valid argument, and that's why I put it in the homework. So this will help you with that. So we're going to let theta live between 0 and pi, kind of thinking that this is going to tie into the inverse cosine eventually. Now, what I want to do is just show you something here. Let's just look at some graphs. I'm going to look at the sine graph from -pi/2 to pi/2. Again, thinking about that. And we'll just mark off -1. We're just going to look at this in terms of shifts, because when we define these functions, we noticed that the cosine and the sine were just shifts of each other, but we had some flexibility as to how we wanted to define the shift. So in this case, I'm going to draw in this piece of the sine function. So here we have sine of theta. And of course, again, we're being a little bit flexible because I'm just going to focus with this one on the cosine graph. Now, look at this, and I want you to think a little bit. If I shift this graph to the right pi/2, let me draw what I'll get. So right here, we'll shift this point over pi/2 radians. We'll shift this one over pi/2. So if you want, go ahead and just mark this in so we have some way of knowing where the pi/2 is coming from. Obviously, we need to discuss pi/2 because it's in the lemma, and that's pi, of course. And so now if we shift this point over, we are at the axis, the y-axis, out of the quadrant, so to speak. And so we can draw it. Okay, now, what is this function? Well, it's interesting. We think of the cosine, we'll start here and go this way. So what we have generated here is the additive inverse of the cosine. That is the reflection of the cosine in the x-axis. So here we have the negative of cosine of theta. So if we shift the sine function to the right by pi over 2, we actually get the additive inverse of the cosine function. So here's an identity based on how we define the functions. And then, of course, using our transformations from college algebra. So sometimes what we have to do is think about our definitions and then come up with an identity that hopefully will help us get to the actual answer. So now we have sine of theta minus pi over 2 equals the negative of cosine of theta. So now look at this and see why this is coming together. We again have to respect this little sidebar here. So now, of course, if theta is 0, we get negative pi over 2. And of course, if theta is pi, we get pi over 2. So we're seeing that we're respecting the ranges and the domains here. And that's imperative. The idea of, I've worked this argument several times with my pre-calculus classes, and students will say, well, what if I use this? This is true. And it may very well be a true identity. However, if these restrictions are not respected, it's like we're in the twilight zone. It's like we're working with functions that don't exist because our functions have to respect the ranges and domains that we have defined for them. So that's the tricky part with the inverse trig functions. But once you adopt and accept the definitions of them, then it's easy. And that's how I want you to see this. So now when we look at this, we're thinking, how can we move this forward to end up with an equation like this? And the key is to apply. So we're going to use our inverse equations, and that's why I spent so much time on those last lecture. So apply inverse sine. So we'll do that. So we're going to have, and I'll keep using the blue here. So we have inverse sine of sine of theta minus pi over 2. We just have more stuff. Remember, last time we just used an x, and so it was a whole lot less writing, but it's the same thing. This is taking the place of the x in our last lecture. And of course, now we have inverse sine of the negative of cosine theta. Now, like I said before, this is going to make sense because this argument, or x, lives here. And we need that restriction if this is going to absorb, that is, if the inverse sine is going to absorb the sine, the theta minus pi over 2 must live in here, and it does, as we just verified before. So this is valid, again, using the inverse equation. So on this side, this what? Reduces to theta minus pi over 2, or just the x, as we wrote in the last lecture. And now, and we're actually going to prove the result that I'm going to use here. Remember, one of the major results of the inverse sine is that it is an odd function. And so now we have the inverse sine of the negative of cosine, so the negative will factor. So we have the negative of inverse sine of cosine theta. So I'm going to write over here in red, inverse sine is odd. So that means the negative will factor, just like the standard sine function is odd. Okay, now we look at this and say, okay, we've got this, and we've made a big stride forward, and we go back up to our equation, and then we say, okay, now using the theta, we can define the x. Okay, so how you state your lemma really depends on what kind of variables you're going to use. I need to pick a variable here that's not the same as x, so I wouldn't say let x be an element 0 to pi. That would be just unclear, so to speak. when we say that an argument is unclear or ambiguous, that means maybe we've used a variable two times in the theorem proof, and they have different meanings, and so that doesn't make sense. So unfortunately, sometimes we're very lazy with our notation, and we can be flexible enough to not write things that are completely wrong. But here we see now that we have a definition for X. So this will imply, as a little sidebar, let X equal the cosine of theta. Now, of course, this is good because cosine of theta lives between -1 and 1. That's just the basic cosine function. So that corresponds to X. So that's a check, right? And so now if we apply the inverse cosine, we see that theta is equal to the inverse cosine. This is how we defined the inverse cosine function yesterday, inverse cosine of X. So now we have our hands-on inverse cosine of X, but we know the inverse cosine lives where? Between 0 and pi. And so that was convenient. So you have to think about this argument. WebAssign didn't do as much detail as Professor Ron, because I think what they were trying to do was just kind of give you some steps to think about, maybe to introduce it in a more subtle way. But mathematically, that's where I come in. I give you the additional detail that you need. So now we see that this pairs up exactly to where we started, and this is a check. So this is what I'm talking about, ladies and gentlemen. When we work with inverse trig functions, we must respect the ranges and domains. And if we get to a point in the argument where one of them may be violated, then we have to stop, because then we're writing down nonsense. So this is the key, and this is why I'm bothering to do this. If you're ever going to have any success with inverse trig functions in calculus, you need to know this, and you need to understand how it works, that it's based on a definition. So again, where most math students think, oh, I can study math 30 minutes, before the test and be fine. I'll spend all my time on chemistry and history. That's not good. Okay. So I've said many times to students, if you are in STEM, your mathematics requires the most of your time. And if you are not doing that, then you need to change it. The ultimate backbone of any STEM career is mathematics. Okay. And so maybe in your science classes, you can use your fancy calculators and your computer algebra systems, but not in mathematics. And when you get to the university and you take tests and they say, okay, here's a pencil and a sheet of paper, go to it. Oh, and here's the test. You have 45 minutes. So I'm just saying, spend the time on the math. So now we can go back over here and make some substitutions. Theta is what? Inverse cosine of X. Pi over 2, well, that just is what it is. And now we have the negative inverse sine of cosine, which we've defined to be X. Now all we have to do is transpose the sine, inverse sine function to the left and the pi over 2 term to the right. And so we get inverse sine of X plus inverse cosine of X equals pi over 2. So this is a way to justify an identity that I gave you. And then when you get to calculus 2, you're going to use this equation to figure out why the derivative of the inverse sine is the negative of the derivative of the inverse cosine. This will be very useful in calculus 2. And that's why you'll spend more time on inverse sine and not so much on inverse cosine, because the derivatives differ by a negative sign, and that's not a big deal. Why do you need that? You can just slap a negative on it when you need it. But here's the thing. The trigonometry will definitely impact the calculus of the inverse trig functions. That's a very rich theory in mathematics. The inverse trig functions are truly, truly important objects in analysis. So this is our intro to it, and I hope that it will ring true with you as you go through this. So what I'd like you to do here, again, this will help you do your WebAssign problem, but I want you to work through this and understand it and see how we have respected the range and domain. Again, sometimes mathematics students will say, well, why did we do this? And my answer might be, okay, well, we had to come up with something that would get us moving in the right direction. So a lot of times when you prove something or you justify something, say your science professor says, well, I want you to come up with a plan or a model to do this. And so you don't really know what to do. So you put something on the drawing board and start with it. Maybe it doesn't work and then you have to try something else. Well, math is the same way. You'll say, well, let's start with this. And then we do, and like we've got a nice identity like we have here, but then we get to the halfway through and then we're messing up with the domains and ranges. And so, well, we got to go back to the drawing board. So it's the same thing. So we have to respect, in science, you have to respect the experiments and the science. In mathematics, you have to respect the definitions. It's all intertwined. Okay, now what I want to do is say something about the inverse sign being odd. Let's go ahead and justify that, and then we'll start talking about our arc length. What comes after this is certainly easier, but this is not hard if you go ahead and learn, like I say, the definitions of these inverse trig functions. Now the next lemma, you're thinking, do you have to prove everything? No, that's not the intent. I just want you to see how these things are connected so that when we move through the next chapter and then on to 7 and we're doing all those identities and all the uh, uh, equation solving, we'll have something to work with. We'll have a basis to draw upon. So the next lemma will be inverse sine. Again, you can call this arc sine, but you can see why I like the -1. I prefer that. It's easier to work with, but use whatever you like. The inverse sine of the additive inverse of x equals the additive inverse of inverse sine. So again, we say inverse sine, I'll write it out kind of formally, inverse sine and put in all the words, is an odd function. So usually I just say it's odd, but I'll just go ahead and write the whole thing out. We get lazy and we just say even and odd because we don't want to have to write so many words, but go ahead and write that out in your notes. So when you look at this, again, we need to make sure that we obey the restrictions of the inverse sine function. So as a little aside, as we have before, we know that x will live between -1 and 1. You write this down enough times, ladies and gentlemen, you will remember it. And the inverse sine lives between, well, we kind of need an argument, right? Let's put an argument of x there. The inverse sine of x lives between -pi/2 and pi/2. So again, we're just reading the unit circle backwards. And sometimes I wish it were that easy, but at least that's a way to think about it. So when we think about this, we say why. Now, sometimes when you look at this argument, you're thinking, well, maybe this one might be a little bit easier than the last one, since we had to kind of think about how cosine and sine are shifts of each other and come up with an identity that will work with the ranges and domains. In this case, we're thinking maybe we'll just kind of keep going around in circles until we get where we want to go. Now, I will make a comment here. When we define the inverse function, that takes us back to the inverse, which is just the regular sine function. So you're thinking, we're probably going to have to use the fact that the sine function is odd, okay? Because it's just like going between a base A logarithm and the base A exponential. We have to respect how we go in between and how one is equivalent to the other. So now what we can do is just like we did before, let's introduce a new letter, and I'm just going to use beta. Let beta be the inverse sine of the additive inverse of x. Okay, so the idea is that we want to convert this to a sine equation, use the fact that the sine is odd, and see if that can take us back to this equation. That is, we can actually show that this is identical to this. So it's like we're going to go forward, then we're going to go backwards and keep our fingers crossed. So now, by definition, we can apply sine to both sides. Let's just go ahead and do it. I'll go ahead and write it all out. Sine of beta equals sine of the inverse sine of x, or negative x. So now, of course, if we look here, and this is what's so nice about this, notice that if x lives here in this symmetric interval, negative x does also. Because when you got the symmetry about the origin, if you run the negative through, you're still going to end up with a -1 and a 1 with the same interval. So this automatically gives us, which is very useful, that the negative x also lives in there. So that's a check. So again, when you hit the inequality with the negative, you flip everything, but then you get the -1 and the 1 just like you had before. So if x lives here, so does its additive inverse. And so now when we look at this, we see that the restrictions are satisfied. So this can collapse to just what? -x. So this is -x. So this is using the inverse equation. So again, a lot of times when you work with inverse trig functions, you probably just throw this, students will just throw all this to cautionary wind and say, I'll keep my fingers crossed that it works. And many times it will work, and we won't be so formal about things, but we need to start out formal so that when you are less formal, you will at least get answers that are reasonable. So now, if you look at this, you can see that, okay, what does this say? Let me write it over here where we have less clutter. We have what? -x equals sine of beta. So I just repeated this here. So now we can actually solve for x. We need an x, right? So let's solve for it. So let's multiply both sides of the equation by -1. So this will give us x equals the additive inverse of sine beta. Okay, so now we see that this a little bit easier than the previous proof. Now what we can do is, like I said before, we can use the fact that the sine function is odd. Normally, we're taking the negative out of the argument and moving it forward here. Now we're going to go in the reverse direction. We're going to move the negative into the argument. So this will be, and I'll write this in red, sine is odd. Sine is odd. So this will give us sine. Maybe I should have done this one first, but I got your attention. So we use the fact that the sine function is odd. Now we've got x equals the sine of the additive inverse of b. Okay, now, so how are we going to get this? Well, now we're good to go. We can apply, in this particular case, the inverse sine function. So now apply inverse sine function. So we've gone forward, now we go backwards. So apply inverse sine. So here's our equation right here. So we have inverse sine of x equals inverse sine of sine of the additive inverse of b. Now again, if b, again, we look at this, b is here when we define this. And so this gives us exactly what we need. We now notice when we're up here, we need for the negative b to be in the range of the inverse sine, which is this, but this is the same argument. If If b is between negative pi over 2 and pi over 2, then we can write this also. We get b, the additive inverse of b there too, by the same argument as we did for the negative x, because it's symmetric about the origin. So we get that check. This checks with the inverse equation. So we can use the inverse equation. Again, we can't overlook this, because if we do and it's not valid, then what we've written is nonsense. So now we can use the inverse equation, and we're just left with the x, which is the additive inverse of b. So this is the inverse equation again. But now we're good. So we've got negative b equals inverse sine of x. So multiply through by negative. So we get b, which is the inverse sine of the additive inverse of x, equals the additive inverse of the inverse sine of x, which is what we wanted to show. So basically what we had to do, we had to move forward applying the inverse sine function, or applying the sine function, use the inverse equation, and then take it backwards. So that means what we had to do was find some way to move that negative sign inside and then outside again. So we start with this and we get exactly what we need. So the beauty is that we're thinking, just like when we do the log and log identities with using the exponential rules, even though it's not the best way to do it, we're thinking, what do we need to start with so we can actually get to the finish line? So we start with this because this is the most abstract object in this equation. We often do this when we do identities with the regular trig functions. We look with the most complicated side and then unravel it to something simpler. Now again, you're thinking there are infinitely many identities that we could probably come up with, and that's true. And we don't use all of them clearly, but there are certain ones that come up all the time. So what, again, I wanted to do was show you that it is possible to verify these particular constructs that we talked about on the last lecture using the definitions of the inverse trig functions. And again, if we do a proof or justification, we must respect the range and domain. And again, it's not overly difficult. I'm not using anything but basic algebra. I have not done anything here except algebra 2. And then, of course, we threw in the definitions of the trig functions. That's the only new thing, but that's not anything more than a definition. So when you look at these arguments, it's a way of putting things together that will get you to the finish line. I always say the finish line because there are many ways to do it, but we have to be a little bit more selective about how we do things because we only have so much information. Right now, we just have the unit circle. Later on, we're going to have the imposed right triangles, which will illuminate things a little bit more. So again, as we continue to work through the trig, you're going to see, that makes sense because that's consistent with what we proved about the complementary angles. Oh yeah, I'm using the odd nature or the odd characteristic of the inverse sine. Oh, we proved that. It's like, oh good, that works. So at least I don't want you to feel like we have to accept everything without any justification. I mean, after a while, you might think, well, I'm going to forget all of this. You won't forget this if you work back through it. And if you work back through these arguments, it will help you to understand how we respect the definitions of these functions. So very good. So inverse trig, there's our introduction, and it'll take us a long way. You might be surprised, but it will take us a long, long way down the road. And that's all we need. Now, what I want to do is say some things about arc length, sector area, give you a way to compute degree measure if you have a radian measure, and then say a little bit about circular motion. So this is like physics class today. So this is 6.1. So we'll have arc length, and this will be relative to a circle. you will do the more general arc length in calculus 2. Arc length, sector area. And again, the first two will just be relative to the circle, okay? And then we'll talk about degrees, and then maybe a little bit about circular motion. So when it comes to arc length for a circle, we're gonna think about how we can make a connection or identification between measurement along the unit circle and the abstract notion of an angle. And this is easy. Now, this is more like probably what you remember from geometry. So we're going to go back to the unit circle right now. So go ahead and draw a unit circle. So here's our unit circle. Of course, I'm not following all of the tick marks here. So that'll work. It again, not Rembrandt, but it never will be. Close enough. So now what we want to think about, if we've got S1, remember S1 is just basically the unit circle x squared plus y squared equals 1, our friend, x squared plus y squared equals 1. And so if we think about a terminal point, we think about a distance from 0, 1 along the circle. Let me just mark this off. Excuse me, 1, 0, not 0, 1. And we've been calling this distance by the letter T, just for convenience. And then of course we call the X coordinate of the terminal point X, and we call the Y coordinate of the terminal point Y. And of course we call those cosine T and sine T respectively. Okay, so, and then of course we can use any variable you like. Now, what we're going to think about is here for this 1, for the unit circle, we're going to think of this abstract measure from the x-axis to this radius as an angle. That is, we're going to call this theta. And theta will be the abstract measurement from this particular ray, so to speak, to this ray. That is the x-axis, positive x-axis, to the radius. And so we're going to think about theta as being identified with T in the unit circle. So here's what we're going to do. We identify this is the word we use for it, angular measure theta with the distance T. So we think of theta being connected or identified with T. So if T were pi over 4, we would say theta was pi over 4 based upon the unit circle. So again, there's no difference. And the angular measure is actually quite abstract. When you think about distance, when we started with distance along the unit circle, that's easy. You can think, okay, I can walk along here and got a nice distance. So in order to introduce an abstract idea of a object that we call an angle, we have to identify with on the unit circle, the T, with this new object theta. Now, of course, theta I just use as a label for it. You could call it anything, alpha, beta, gamma, whatever. It doesn't matter, phi. So we have this relationship here. Now, what we want to think about is that what if we had a circle that was not the unit circle, that is arbitrary radius. So consider a circle with arbitrary radius r. Maybe the radius is 2. Maybe the radius is 1/2. Maybe the radius is 10, okay? Not the unit circle. So what we want to do is say, okay, if if we change the radius, how is that going to impact the relationship or the identification that we have between theta and t? And it's very easy to do. So now we define the arc length to be S. So we're going to use the letter S as a replacement for T and not worry about the T anymore. S is the common letter for arc length. So if we think about this, if we think about, say, theta, if we start here and we lap once counterclockwise and we have one traversal, that would be 2 pi radians. So we'll say 2 pi radians. Again, now we have a arbitrary circle, and then we think if we lap once around, what is the actual circumference? Well, we know that will be 2 pi times the radius, or pi d, or 2 pi r. So we have 2 pi r. So that's a proportion, or actually a ratio of the angle to circumference. And so now what we want to do is say, how can we get the connection between now the actual angle and the arc length that we're going to define to be S? Well, we set up a proportion. So now this ratio must be maintained because we're working with a Euclidean circle. So if we have an arbitrary angle theta now with the arbitrary arc length S, this proportion must be maintained because again, we have a Euclidean circle, and as we broaden out or compress, so to speak, we're still maintaining that ratio because we're not deforming the circle. We're taking it and making it uniformly larger or uniformly smaller, maintaining this particular ratio. So now what we can see, and you're thinking, well, this is so simple. The two thetas will absorb, and we get 1 over r equals theta over s. And now we can just cross multiply. So s will equal r theta. So now we're thinking, oh, okay, remember now S stands for T, and we're thinking if the R is equal to 1, we would just get S equals R, or the T equals theta, like we had up here. So this is consistent with the unit circle, but now this reflects the fact that if R is not 1, this is the factor that we need. We actually need the magnitude of the radius. So in general, if we're considering length along a circle and arc length, the circular arc length, then we're going to see that S will be R times the actual angle theta in radians. Now, back in geometry, what you would call theta would be a central angle. That is, if you're thinking of an angle that's formed based upon the center of the circle, you think of central angle, and that's a good term to use. So now we can take this identification and make it more general. Now, what's important here is we're using the pure measure. So I want to say theta is measured in radians. This is easy. I mean, this is one of the easiest formulas we've had so far. It's measured in radians. So this is very important. We have to use the pure measure of the unit circle, okay? So don't make that mistake. We're only thinking about radian measure. That's why I'm doing this first. And the construct of the abstract angle is something you talked about in geometry. So that shouldn't be very difficult for you, but you can see an angle is so much more abstract than a length measurement. But we make that identification and then we say, is that good? Can we extend that to any radius? And we can. So, and it's consistent. What we get here is true here. So they toggle between each other. Now, the only other thing that we can easily get at this point is we think of this little wedge here. We think of, okay, that's a wedge of a circle based upon the central angle. how can we compute the area of that? And that'll be easy to do too. So let's draw another circle. And again, this will just be arbitrary now that we have the arbitrary understanding. So now, again, another formula for the formula card that makes the formulas for the inverse trig functions seem, this seems simple compared to that. So now we just have a circle of arbitrary radius. Let's see here, that needs to be down just a little bit. So let's draw in our arcs. Okay, there's our circle. Now what we want to do, again, we'll just draw in a terminal point here and connect R. I have to be as fancy as we were before. Here's a radius R. And then we have a central angle theta, just call it what it is. And now what we can do is shade this like we're in a calculus class or high school geometry. So what we want to think about now is a sector area. That is, we call this sector of the Euclidean circle. So if we look at this, we're thinking, okay, we use the letter S for arc length. What do we use for sector area? Well, usually we call it A. So we'll just say let A equal sector area. So when we think about this, we have sector area, just like we had in this case, an S, which corresponds to theta, and we'll say that this corresponds to theta, just like we have S corresponding to theta. So we just say sector of Euclidean circle, A designating the area of corresponding angle, central angle theta. And so now we're going to use the same trick. Okay, so if we think about an arbitrary circle, and of course we haven't had a calculus class, so we'll have to use our formula from geometry. If we traverse one time and we think for that particular measurement, we have an angle measure of 2 pi. So we have 2 pi. And we're thinking about, we're either going to uniformly enlarge the circle with a radius bigger than 1 or compress it with a radius smaller than 1. And so what is the corresponding area of the circle? Well, from geometry, we need calculus to prove it, but it's pi r squared. So again, we'll say pi r squared. This will be the central angle or angle, and this will be the area. Now, this ratio has to be maintained if we simply just chop up the circle. And we're doing this in a way when we're talking about radii. So for instance, we're thinking we could do half of the circle or maybe, an eighth of the circle or something. So how are we going to set this up? We're going to do the same thing we did up here. We're going to have the arbitrary angle theta, and then of course the arbitrary area, which will depend on the actual radius that we have for our circle. So now if we look at these two things, they look very similar. The only difference is that we replace circumference with area, and therefore we replace S with A, the thetas being the same. So now you're thinking, how simple is this? Okay, well, the pi's absorb, and we get 2 over r squared equals theta over A. So now, of course, we can cross multiply. That's one thing you learned in general math that we're lucky still works. So we have 2A equals r squared theta. So now, of course, if we divide by 2, we get an area for the sector or formula for the area of the sector. So we get 1/2 r squared theta. So I probably could have done this the first day of our trig lecture, right? Because this is really very straightforward and very simple, and it really just appeals to what you learned in your high school geometry. Now, another thing that's very important, I've got this in a blue box here. Theta is pure measure. It's measured in radians. Same thing goes for here as we've done in our construction. Theta is measured in radians. So we need the pure measure of the calculus, which requires the radian measure. That is the dimensionless measure. You know, we call them radians, but there is no dimension. When we write a number, you know, we'll say theta equals 2, okay? We mean by that 2 radians, okay? 2 radians. And then you think pi is approximately 3.1416 radians, okay? So two would take us into the second quadrant. So when you identify, and it's nice when it has a pi in it, if it has a pi in it, it's a little easier to figure out where it is because we have the 2 pi, you know, for the circumference of the unit circle. But again, when you have an angle equal to a number and that's it, that means radian measure. It doesn't mean anything else. And so we see the dimensionless quantity set equal to an angle, we know that's radian measure, always. That will never be a source of confusion. So just remember, as we do arc length and we do sector area, we use radian measure. Now these formulas are simple, very easy, and not even that difficult to remember. But all we do is use basic constructs from geometry. So nothing new here. This is all old, and you probably learned these formulas when you were in high school geometry. So maybe this is kind of boring. Okay, now what I want to do, and we'll have an opportunity to use some of these. I want to go ahead and define what we mean by degree measure for an angle. Now, you're thinking, we have, you know, we got radian measure. Why do we need something else? Well, your common sense tells you when you were growing up, no one ever told you about radian measure. Someone might say, "Oh, well, that's a 45-degree angle, or that's a 90-degree angle," and so you grow up hearing degrees, thinking, "Oh, well, that's the way we do it." Well, that is a human convention. So let's think about what that means. So this is what we want to talk about now, and this is again very easy, but very important. Degree measure of angles. When I say things are easy, it's like when I teach calculus, I'm basically saying that this is something that you don't really need me for. You know, and you don't have to worry about it. That doesn't mean that it's unimportant. It just won't be as abstract as some of the things we talked about. So when we think about degree measure, we think about the human construct. We take the unit circle and we just think of chopping it up into 360 parts. So we divide, well, I was going to say define. Let me just say this. We divide the circle into 360 parts. So if you think about that, you know, you really do have to identify that with the measurement along the circle. So you think, you draw your circle, and you've got your center here, and you think about this, let's think about maybe a angle measure, in this case, of pi over 4 radians. So say we have pi over 4 radians. So when we think about the circle, you know, we know, and if we move around once, that's 2 pi radians. And of course, we chop up 2 pi, we divide it by 12, you know, we divide it by 8, 4, 3, whatever, you know, we get all these interesting fractions of 2 pi. Um, and we're thinking those turned out to be very useful and were easy to compute terminal points. So now we're thinking, what's this degree measure? Well, it's something that we invent. So what we want to do is if we divide the circle basically into 360 parts, that's actually going to be a division of 2 pi. So we just use those two numbers to figure out how we have the basic conversion factor. So here's what I'm going to do. So with this and thinking about this, we will imply this will be equivalent to the following. That is, we're going to think about theta, and I'm going to use DEG for degrees, okay? And then we're going to think about theta in terms of radians, and I'm going to say RAD because lazy, right? So we're not going to write out degrees. We're going to just say DEG, and we're going to think RAD for radian measure. And so just like we did with the arc length and the sector area, we're going to create a proportion. So now we're starting with the abstract and moving to the less abstract. So if we think about an angle going all the way around in degrees, we're going to say 360. And we're actually going to use a little circle like that, okay, for degrees. I didn't make this up, so don't be mad at me. And then, of course, we already know if we go all the way around once, that's 2 pi radians. Right there. So now, and then of course, sometimes you can relax and leave out the degree symbol because you know if you've got degrees, you've got to put the degree symbol. So if you leave that out, no big deal. Just remember to put it in when you actually state it. But again, the 2 will absorb into the 360. So this will be 180 degrees divided by pi. So that'll be a conversion factor. Now, again, this is really important because if I said theta equals 2, that means theta is 2 radians, ladies and gentlemen. And if I say theta equals 2 degrees, that's a big difference. So if I mean radians, I do this. We say radian measure, radian measure. Here we say degree measure. I'm not trying to make you feel like you're in the first grade, but there's a big difference. So if you're doing a WebAssign problem or you're doing a math problem on a test and you're asked to give degree measure, then you've got to put that symbol there. Otherwise, it means that, and that's not the same thing, okay? Again, very simple, but you would be amazed when I get questions from students that say, well, I know I did this right, Professor Ron, and it's marking it wrong. I said, but what's the measure? Okay, so the symbol that we use is the little O, so to speak. And I think the WebAssign actually has a symbol for it. So just remember, if you use degree measure, you have to denote it with that little superscript O. Okay. Now, what does this mean? Okay, well, now we've got conversions. So theta in degrees is just now, we've got what? 180 degrees over pi times theta in radians. That would be, well, if you've got this, you've got all of it, but let's just do the separate equations. And then, of course, theta in radians. Again, if you want to do that, we can just flip everything around. We get pi 180 theta in degrees. Now, of course, you can leave all this degree stuff out and just write the actual values for the degrees and leave the little circle out in the conversion formula. That's fine. I'm not going to be bothered by that. But what I'm trying to point out here is that if you have converted to degrees, then when you write the actual angle, it must have the little superscript O. Okay. If you don't put it in the conversion formula, that's not going to be a problem. You're going to get the correct number. But it's like being in physics class. Do you mean this or do you mean this? And so I don't want this to be a stumbling block for you. So I'm making a big point about it. Now, when it comes to degree measure, you all are professionals. You probably know more about degree measure than Professor Ron because you've grown up with it. And me being a math professor and an analyst and someone who deals with, again, real analysis and a lot of number theoretic constructs, pi uh, radian measure is what I think all the time. And so again, this, if you look at Professor Ron's unit circle, you'll see that I have the radian measure and the degree measure. And so, of course, the WebAssign will give you some practice converting to degree measure forward and backwards. So that's a real easy construct. But let's just look here and just say, okay, we've got pi over 4. We know what it is. We know it's 45 degrees, but let's just prove that. So now we can say theta in degrees and use our conversion factor. So this will be 180 degrees, pi radians. And so here we've got pi over 4. So again, we have radians, pi over 4, and we want to convert to degrees. And so, of course, like I say, if you don't put the little superscript up there, that's okay. Just remember to put it in at the end, or you can do as I've done here. It's no big issue. The pi is absorbed, and we have 180 degrees divided by 4. But now if you look at this, and this is easy to do, we can divide by 4. So 4 will go into 18 4 times. And then, of course, we have a 20, so that gives us a 5. So we've got this many degrees, divide by 4, and that leaves 45 degrees. So again, if you don't want to tag the little degree symbol along the whole way, that's fine if you don't include it. I don't normally do it, but I've started doing it because I get tired of the fact that my students don't put the notation when they actually answer a question. So now, if that will help you remember it, do. Like I say, usually I leave that out, but I'm starting to think, it's probably better just to put it in just so my students don't forget it. And so now you can think of, yes, 45 plus 45 gives you the 90 degrees, and then 90 plus 90 gives you the 180 degrees, and then 180 plus 90 gives you 270, and then 270 plus 90 gives you right back up to 360. So now we can easily see that we have 0 radians corresponds to 0 degrees. Pi over 2 radians corresponds to 90 degrees. Pi radians corresponds to 180 degrees. 3 pi over 2 radians corresponds to 270 degrees. And then, of course, 2 pi radians corresponds to how we started the ball rolling, 360 degrees. So again, this is a very simple construct, and maybe, again, is something with which you are more accustomed because of your work in geometry. Now, of course, in high school geometry, I'm almost pretty sure you start talking about circles and things, and then you get the pi measure, the radian measure. But when you're working with the triangles, you're probably introduced with degree measure. You've got the 45, 45, 90, and the 30, 60, 90, which we'll talk about later next week. But the idea here is that these particular types of measurements and degrees are very convenient. They are part of our culture. Everybody knows what you mean. When you walk up to someone on the street and you say 90 degrees, they know exactly what you mean. If you say, oh, can you draw an angle pi over 2 radians? unless they're a STEM major or an engineer or a math professor or a STEM person in general, be like, I'm not so sure about what that. And then you, of course, mention, oh, could you do 90 degrees? And they know exactly what you mean. So it's a part of our culture. We don't think metric system in America. We think the English system of weights and measures. Like I said before, when I was a little kid, I was told, oh, we're going to go to the metric system. We're going to the metric system. And we're not. We never did. We're still using pounds, inches, we miles. We do. That's how we do it. So whatever. I thought it was interesting. All the adults told me what we were going to end up doing, and it never occurred. Okay, so just like with the degree measure, you can mod out by 360 and you can add 360 to get coterminal angles, and that's very, very simple. No difference. We mod out by 360 like we mod out by 2 pi. So it's the same construct altogether. Now, what I want to say, uh, when you're writing your coterminal, like I just mentioned, when you're doing your coterminal angles, I'll just write out some formulas. You can think of theta in degrees plus 360 times an n, where n is an integer. So that's how you can get coterminal. They terminate at the same point, terminal point. And then, of course, that's just like theta in radians. You just do 2 pi n, where n is an integer. So the coterminal angles are just like we've done before. So that's very easy. And again, something that we've exhausted maybe too much. Now what I want to do is say just a little bit and do some examples, say a little bit about angular velocity. And when I talk about velocity and linear velocity, we're going to talk about it relative to a circle. So for instance, relative to the circle, we can discuss angular velocity, and we're going to use a symbol omega. Omega, it looks like a W, angular velocity omega, and linear velocity, we're going to call it nu for like a V. I just use the book uses omega, and I write my V's like the Greek nu, so you know it's a V. Okay, so the ideas here very straightforward, very simple, but you know, when you think about physics and you know think about motion and all, circular motion is something that we see in everyday society. I mean, when you drive your automobile, that your wheels, a circular motion. So there are things that are actually important to us, and we think about them. And so again, this is more like what we do in physics. So what we think of in this case, so here are our definitions. We'll think of angular velocity as being an angle theta per unit time. So this is basically the change in the angle theta per unit time. So again, we can think about a circle. Theta. And we're thinking, how quickly does the theta unravel, so to speak? Do we have like 2 radians per second? Do we have 45 degrees per second? Now, the thing is that we can always write things in terms of degrees, but then if we're looking for distances or anything like that, we've got to convert to radian measure to get that pure measure. Again, the pure measure gives us the measurement of physics. Okay, the degrees don't. The degrees are useful, but we got to do that conversion when it's necessary. So we think of the change in the angle theta, let me put in theta here, per unit time, and t seconds, minutes, hours, whatever. And then we think of, in this particular case, linear velocity. Now, we can see how theta might be unraveling, but then we might be interested in how the distance varies with respect to time. So we might have a corresponding S or arc length. So this will be the change in the arc length per unit time. So we'll say S over T, which will be the change in the arc length. These are just simple definitions, S per unit time. So when we think about this, we're like, okay, well, is this good? And there's nothing wrong with it, but no. So this is kind of standard here. But then we can say, well, S, we'll go ahead and write this again. We know this is just R theta. We already proved that. The arc length is just the radius times the angle measure in radians. And then, of course, we see the omega here. So this is R times omega divided by T. So we have R omega. So now we have the definition, standard definition, but then we have maybe a more convenient definition of linear velocity, which is R omega. So again, there's not a whole lot here, but it's like we're in a chemistry class where we're making sure that the units absorb correctly, and then in the final analysis, we get the prescribed units of the problem, so to speak. I mean, are the distance to be measured in inches? Is it to be measured in feet or miles or whatever? Do we have the correct time units? Or if we just have a distance and the times have absorbed, I mean, are we correct with that dimensional analysis? Now, one thing that we often find in the circular measure is the construct of a revolution. So we'll say 1 revolution, just like we did before when I was talking about traversing the unit circle one time. 1 revolution corresponds to 2 pi radians. So sometimes what we do the abbreviation and we say 1 rev corresponds to 2 pi. So if you're given a problem where you have a wheel that rotates at a particular number of revolutions per second or per minute, then in order to convert to the actual distance traveled by, say, a point on the tip of the wheel, like right here, then we would need to use this conversion factor. Revolutions are like degrees. They're convenient, but they don't provide the pure measure. We have to move to the pure measure by a correct conversion factor. And another thing that's important too, that we'll see in these types of problems, we'll say 5,280 feet will correspond to 1 mile. And of course, you think, you're not in the first grade or the fifth grade, but this is a construction or a equivalence that we often use when we're doing these types of problems. And of course, all of you science and biology experts, the metric system and all of that very well. And your constants, Avogadro's number and Planck's constant and all the, the universal gravitation constant from physics. You all are very adept at that. So I'll let you continue to be wonderful at that. I'll just make sure that you're doing your math correctly. Okay, so let's look at some examples of this. So again, all of these particular definitions are very simple. So like I say, when you work through these problems, you're going to actually enjoy yourself. They're not tedious. So let's look at an example of this. And then, of course, we'll do the famous Alonzo's tethered cow. I'll tell you about that when we get to it. I had a former student who thought the problem was neat. And I said, okay, we have to name this problem after my student Alonzo, but I'll tell you more about that. So we have a car wheel. We have a car wheel that has a diameter. Diameter is 28 inches. Okay. And then we have, and this is why I've introduced the last conversion factors. We'll say what distance is traveled. Of course, we'll use the English. You know, in Great Britain, we use the American. In Great Britain, they use traveled with two L's, and that's considered correct. But in America, we usually just use one. But I think it's interesting how spellings change from country to country. If the wheels rotate, and in this case, 10,000 times. And of course, we'll assume that we're not driving in the snow, so there's no slipping. So another thing that's interesting about these problems is they're not very difficult, but if we use exact computation, we can get an exact answer. And then, of course, if we need an approximation or whatever, you know, you're in a physics class or whatever, you can actually do that. So now what we want to do is say, okay, well, we have S, that's going to be the arc length, will be R theta. Now, what we have to do is think about, okay, well, you know, R is the easy part. R is 1/2 of the diameter. So we can think R theta. So we have 28 inches divided by 2. That's the radius, okay? So that was the easy part. And now we need theta. So here's what we have. We've got 10,000 revolutions, and we know 2 pi radians per revolution. Now, here's one other thing that the question asked. What distance is traveled? And we want to write our answer. I'm sorry about this. Write distance. That's why I gave you all those conversions. Write distance in miles. Okay, so there's another little tidbit that we're going to need to worry about. Okay, so when we think of the theta, we've got what, 10,000 revolutions. And then we have 1 revolution for every 2 pi radians. Okay, so that gives us, this gives us an arc length in inches. Okay, so we think about, okay, if we revolve 10,000 times, we have to have a conversion factor of 2 pi. Of course, the revolutions will absorb. 2 pi is pure measure, and that's inches. So that'll give us the number of inches. But if we want to convert, and here's something that you can do, ladies and gentlemen, you can just write your answer in inches and then do the conversion later to miles, or we can do it all at one time. So now let's go ahead and write this out. We've got inches here. So we have 12 inches, and that'll be 1 foot. And now, of course, we'll use the conversion factor, 5,280 feet in 1 mile. So this part you can do after the fact if you want. It's not required to do it at the front, but that's usually when I do it. Again, just think about being in a chemistry class. And so here's what we can notice. The inches absorb, the feet absorb, and we're left with miles. Again, notice we have the correct dimensions, miles. And I was noticing on tests where people were putting all kinds of slash lines through things. Please do not do that. I get so tired of your work being cluttered with unnecessary writing. Okay, just don't do that. I mean, I look at that and I think, does anyone listen anymore? you can easily see that these absorb, and then you can go back and check your work to make sure that your dimensions are correct because you haven't marred it up with a bunch of unnecessarily strikeout lines. That's the most absurd thing in the world. And I don't understand it. You can underline them if you want, but don't use any more slash lines. That is poor notation. And when you use them, it is a complete show of disrespect. Okay. So just remember that the next time you feel like you need to put in a slash line. It is it is poor mathematics and completely unnecessary. Now, if we look at this, we're thinking, okay, well, let's go ahead and be cheap. The twos will absorb already, so we can put boxes. This is what I want you to do. I want you to make it nice and beautiful. Use boxes. That way you can go back and see everything you've done very clearly. So now, and the units are fine. We have miles, so we've got 28. So we move down, we've got 10,000. The two absorbed here, so we've got a pi. So notice we have 28, we have the pi, and then these are all ones. So we're done with that. This is miles. Now, if you don't want to write in your miles here, you don't have to, but we can just stick that there. And then downstairs, what do we have? We have 12 and a 5,280. So now if you like, we can go ahead and reduce some things. Of course, the zeros will drop out here. So use Professor Ron's technique. Use the boxes. So I can exactly see what you're doing and I can check your work when you're doing your calculations on your test. And now what we want to do is go ahead and rewrite the 28. Notice these both have fours in them. So this will be a 7 times a 4. And this will be a 4 times a 3. And then, of course, here the zeros will go. So we have 1,000 divided by 528 miles. So now the 4s absorb. So this gives us 7 over 3. Now what we can do, we can just break this down little by little. Let's just go ahead and take out some 4s here. So we have 4 times, of course, 250. And then 4, here we can divide, that'll give us a 1, then we have a 12, that'll be a 3, and then a 2, 132. Just keep the numbers simple. These absorb, and this is miles. So now we have 7/3. And then of course here, if you look at this, we can go ahead and reduce by 2. So we'll have 2 times 125. And then of course a 2 here. So that'll be what? That'll be a 6 and then a 12. So that'll be a 66. The 2's absorb. Oh, and of course, dear old pi out here. Don't let me not forget pi, our friend pi. Sorry, pi. Yeah, pi is always hanging out. So let's not forget pi. So now notice everything's relatively prime, so to speak. So we have what, 700 plus a 7 times a 25, that's a 175. So that's an 875 pi. And then of course we have a 3, so that's going to be what, an 18, and then a 1, so a 198 miles. So that's exact. So the idea here is that this is just exact computation. So what I'm trying to do is give you a way to notate your work that is more professional. Okay? Use boxes or underline or put little checks. That way I can see your work. I can see your work. You know, it's just a matter of making your work look professional. Okay? You are a future STEM professional. okay? Your work needs to show integrity, all right? We are not perfect. We are human beings and we have many, many, many faults. I certainly do, okay? So what I'm trying to help you do is to have you lay out your work in a way that's clean. That when I see your test work, I'm like, excellent. That looks like some good test work. Clean, easy to read. Doesn't have to be perfect. I mean, you don't have to have everything perfectly notated, but the nice thing about this is if we write it neatly, we can go back and check, well, what happened to pi? Pi didn't absorb. Well, it's right there. Well, let's remember it. Okay. And of course, if you need, if you're on a test and you have an exact answer, that's fine. If you're working a problem in the book or the WebAssign and you need an approximation, then you can use your Google calculator. Now, let me, now I want to do the Alonzo's tethered cow. Then I'll go back to another exercise that we can do also. So let's do that one. So this is a good example of just the basic dimensional analysis using ArcLink and using some of the, again, put all those conversion factors on a note card, or you can use the WebAssign formula sheets or Professor Ron's formula sheets. I think most students find that when they make their own sheet, it's a little bit more user-friendly. Okay, so here's the next example. This is entitled Alonzo's Tethered Cow. And I told my student, I said, that's the name of a new steakhouse. I said, you need to invest in a new steakhouse. But you've got this tethered cow that is tethered in a pasture that has a building, and you're asked with this tethered cow, you're thinking, what is the possible area for that cow to graze? And so you're thinking about extending the rope as far as you can all around that building, and you're going to form a bunch of circular arcs, and you will add up the arc areas to get the grazing area. So Alonzo's tethered cow. So here's how it looks. We've got a building, and this is in your WebAssign. This is an excellent example. So we've got a dimension here of 50, this side. And then we move down. This is a strange looking building. And of course, we've got a lot of right angles. So I'll just trim this off a little bit. So this dimension here, this is a right angle. We have 60. And here we have another 50, again, not to scale, clearly, whatever. And then we've got the tethered cow. So if the cow that was extended, the rope, this would give a distance of 100. 100. And all of this, ladies and gentlemen, these are all in feet. So the measurements in feet. And so now here's the cow at the point right there. I'm not going to draw the cow because I don't want to disrespect the cow. That would not be nice. So we're thinking the cow with the extended rope here can move this way and can also move this way. So first, let's look at the largest arc that it could live in to graze. So we'll just extend here just to use a dotted line. So we're thinking we'll just move, the cow's moving this way in a circular arc. Like this. Okay? So we can call this A1. So the cow can graze all through here with this arc. And notice again, we have an angle of pi over 2. We're going to get a bunch of angles of pi over 2. And then of course now, say the cow is like, I'm going to venture out over here. Okay, so we'll extend this side of the building. So just go ahead and extend this part. Now, as it moves over here, notice when we get to this point, we've chopped off 50 of this, and this distance right here of the building is 20, okay? But now we see that this new radius is 50 because 50 has been chopped off here. And of course, we have a right angle. So we have another sector here, a sub 2, again, with angle pi over 2. So that's the easy part of the problem. And then, of course, the cow gets bored. Again, this is a 20 here, so we have subtract, in this case, to give us a 30. And so it could move around to here. So we'll call this A3. Again, we have another right angle. So the cow gets upset and says, I'm just going to start moving around. I'm going to find some better grass over here. Okay. And then at the very end, we're thinking here, notice we chopped off 60, and then it can come this way, and we have 40. So when we think about this particular setup here, we have 4 sectors. So the interesting thing about this problem is that maybe the cow would only spend most of his time here. Maybe we're thinking, that he'll get creative. Maybe he eats all the grass here and's got to move over here to find some fresh grass, or over here. So again, you just think about being able to move with the rope extended. Then you get to this point, you extend the rope, but now notice 50 has been shaved off. So this radius is 50. And then you shave off 20, this radius is 30. Here we shave off 60, so this radius is 40. So now you can see we have angles and we have radii. Excuse me. So go into each of these and just write R1 equals 100, theta 1 equals pi over 2. Let's see here, let me move this. Okay, and then here, R4 equals 40, theta 4, again, pi over 2. R2 is 50, theta 2 is pi over 2. Well, I mean, this is kind of simple once you figure out the logic. And then here, R3 is 30, and theta 3 is pi over 2. So we just get a bunch of right angles. So we're getting circular sectors in all 4 regions. So again, when it comes to doing problems like this, maybe not the most interesting problem, but it certainly is a problem that we can do with sector area. So I think it's fun. And Alonzo's tethered cow, I'll remember this problem forever. This was a class I had back in, I want to say it was 2000, gosh, when was that class? 2014 or something, 2014, 2015. It was one of my first honors classes in pre-cal. And I basically just gave this as a homework assignment. And in my regular sections, I actually work it out, but he's the one that said he liked it so much, and that's how it got the name Alonzo's Tethered Cows. So that's the reason for that. So now, we want to compute the grazing area. So, and we'll just call this A. So now we'll have A, and we've got all these areas here, will be A1 plus A2 plus A3 plus A4. Now, of course, there's a lot of simplification here. Remember, sector area is just 1/2 r squared theta. But see, now we have the 1/2 and the theta in each of these computations, and the thetas are all the same. So that makes this computation much more straightforward. So in this case, go ahead and put boxes around both of these. We'll just say factor these terms. That's an easy simplification that will cut down on the amount of work. So we can factor the 1/2, and we can factor the pi over 2 that we have common to all of the areas. So pi over 2. So for A1, we have 100 squared. For A2, we have what? 50 squared. For A3, we have 30 squared. And then for A4, we have 40 squared. Now, again, the squares make it easy, and these numbers are all very nice. So it's going to make for a simple computation. So now, of course, we have pi over 4. Now notice when we look at these numbers here, that's a 10 times a 10, that's a 10 times a 5, a 10 times a 3, and then a 10 times a 4. So these will simplify very simply. So we'll get 10 times 10 squared plus 10 times 5 squared. This is called number theory. Let me do the 10 first. My Cal 2 students have learned how to do this. They didn't take me for pre-Cal, because Cal 2 is filled with tons of arithmetic. So now we've got a 10 squared in everything. So we can factor the 10 squared, which is 100. So this will be pi over 4 times 100. So all of these 10 squares are extracted, and that will leave us with a 10 squared, which is a 100. That'll leave us with a 5 squared, which is a 25. That'll leave us with a 3 squared, which is a 9, and a 4 squared, which is a 16. So now, if we look at this and we think about what we have, the 4 absorbs into the 100 to give us a 25. So we have 25 pi. And now what do we have here? We've got some kind of simple numbers here. And what I want to do is break this up into numbers that will be simple. And we'll do it that way. So notice we've got a 125 here. We can do those separately. And then we've got a 25 here. So we'll write this as 100 plus 25 plus 25. So let's go ahead and multiply out. So this will be pi. So 25 times 100, that's 2,500. And then, of course, these are our friends. 25 times 25 is what? 625. Plus 25 times 25, 625. So this gives us pi. And notice I didn't put the feet in here like I did the miles before. We'll tack it on at the very end. So we have 2,500. So this will be a 50. So we have a 1250. And so now that'll give us a 750. And then we add the 1 and the 2. That'll give us a 3. So this will be 3,750 pi. And then, of course, all of these are measured in feet. So all of these radii squared will give us feet squared. So like I said before, it's like when you're doing your conversion to degrees. If you leave out the little 0 in the conversion, that's no big deal. That's not a problem. Just remember at the end, when you state your answer, that it has the correct units. So now, of course, we'll have feet squared here. So this will be feet squared. So what we're seeing with these problems is that we have a very, very simple set of formulas that make the problems actually very straightforward. But what I want to show you is that as we work these problems, we're trying to set up a standard, because as we get into this chapter, we're going to have lots of computations, and we want to make sure that our computations are exact. And then if we have to go to the Google calculator, we've got an exact expression, which we can then approximate. Otherwise, our calculations get filled with round off error. And then we're just befuddled why things aren't working out. So we really do need to adhere to that exact computation. Now, the very last problem, let's see here. What do I want to do? Oh yeah, here's a good one. This is another arc length type deal, which is very useful. Actually, a sector area, which is connected to arc length. Now here we go. And we live in Houston where it rains all the time. So we have a windshield wiper blade. So basically what we have the, okay, I'll draw a little picture here. I can write all this out, but let me just draw a little picture. We've got this blade. So I'm gonna write out the angle here, which will be 135. So let's go ahead and put in the circle. So let me just erase this, because that's getting into my picture. I'll just move it over. So we have a windshield wiper blade. And so now what we have in this case, when we actually look at the blade, you have a displacement here of, from the problem, 14 inches. And then the displacement from the vertex here all the way out is, let's see, what does the problem say? 34 inches. So the blade, there's an arm here, but the blade part is right here, this distance. So we'll just say the lower end will be 14 inches from vertex, and the upper end is 34 inches from vertex. So when we think about this, we want to know, what is the area that the wiper blade covers? Compute area swept by wiper blade if the angle is 135 degrees. Yeah, let me not write the degree like a 0. And so here, we'll just go ahead and write this in, 135 degrees. So this is similar to the last problem and very good. The circular motion is kind of simple. That's like a chemistry problem. That's not very difficult, but these take a little bit more analysis. And so as it sweeps across, we're thinking, well, we get this smaller sector and a larger sector. So we'll say this implies area equals larger sector area minus smaller sector area. So now again, we got the same thing, and we can go ahead and put the little dot here, dotted line here. So again, we'll look at this. We'll say larger will be R2 theta 2, and smaller will be R1 theta 1. But of course, the thetas are the same. Theta 1 equal theta 2 equals 135 degrees. Now, before we do any of these computations, or we could just go ahead and do the conversion, notice again, the sector area is 1/2 R squared theta. So again, we can factor because the theta is the same and the 1/2 is the same. So factor. So let's look at this. So this will give us 1/2, and then we have 135 degrees. Of course, we're going to have to convert that. So we have 135 degrees, and then our conversion factor will be 180 degrees downstairs and pi. So the degrees will absorb and we'll get the pure measure. And then of course we get the larger radius in this case, which is what, 34 squared. So this is like the last one, but a little bit more complicated in the algebra. We're going to get a difference of 2 squares. And then of course, we've got what, in this case, R1 is 14. So now what we're seeing is that we can approach this problem by taking the difference of the 2 sector areas. So now we can go ahead and break this down. So of course we can do the 5s. So we got 1/2, and then we have 5. And so that will be a 2. And then we've got 2 and then a 35. So that's a 27. And here we have a 5. And then of course here, that'll be a 3. And then we got a 30, so that's a 36. So that will absorb even a little bit more. And now we have a difference of 2 squares. And they've got a bunch of 2's in them, which we could get rid of. I'm thinking, yeah, let's go ahead and get rid of these 2's. So this will be what? 2 times a 1, 17 squared, minus 2 times a 7, just like we did the last time. No need to change the format. So now notice we've got the 9's here. So we have the 1/2, the 5's absorb, and then of course that's a 3 over a 4. So we have 3, and of course, Professor Ron just doesn't want to remember the pi. Pi is a good guy, so don't leave him out, Professor Ron. So we have the 3, the pi, and then the 4. So that's what we're thinking about. 135 degrees is equivalent to 3 pi over 4 radians. And of course, the 1/2 are here that we have. And now, just like we did before, we get a 2 squared in each of these. So that's a 4, which we can factor. And that leaves us with a 17 squared. Now here's what I'm going to do. I'm going to show you a little trick. 17 squared minus a 7 squared. Let's use some algebra. That's a difference of 2 squares. So now we've got the 4's absorb. So we've just got a 3 pi over 2. 4's absorb, so absorb. And then we can write this as a difference of 2 squares. So 17 plus 7, and then 17 minus 7. So we have 3 pi over 2, And this will be what? This will give us a 14. So that gives us what? 28. Oh, excuse me, 24, 14. How funny. And then, of course, a 17 minus 7 is a 10. So we're getting good numbers here. And now, of course, the 2 will divide into the 10 to give us a 5. So we get a 5 times a 3 pi times a 24. So, of course, these will absorb to give us a 5. So now we have what? We've got, in this case, we've got a 15 times a 20 plus a 4 times the pi. Professor Ron remembered the pi this time. So now we've got a 0. So we have a 0 here, and then a 2 times a 15, that's a 30, plus, and then we've got 4 times a 15, that's a 60, times pi, and that will give us 360 pi. And then, of course, inches squared. So when we look at these types of problems, the main thing that I want to emphasize here, and this is why I taught this lecture the way I did, the focus on the fact that when we are doing calculations, like if we're given rotations or we're given degrees, things that are human conventions, okay, we have to convert to the pure measure, which is the radian measure. And like I say, I'll be very considerate about degrees. You know, like for instance, you think we need to string the inches all the way through here. That's not completely necessary. That is, I know you know what the dimensions are, and just not to clutter up the work. Now, of course, your physics professor is going to put in all the dimensions for here and evermore, and that's fine. And I don't want you to be sloppy, but I do not want you to have to worry so much about carrying those through. You could put the little inches squared to the side here if you like, but I'm not going to beat you up about that. I just want to make sure that you have the correct dimensions when you complete the problem. But just remember, just like Alonzo's tethered cow, when you work these problems, go ahead and figure out a strategy and then equip the notation or the formulas with the correct conversions. And then of course, when we've got these nice squared formulas, we have a way to factor and to work out the problems in a very clean way. So these make really good examples for tests with exact computation. Lots of times I'll just request that the problem be given exactly so I can see you actually do the work. So again, remember, enjoy this work because it's very much like physics class. We're not really doing anything that abstract. We did the abstraction of the inverse trig functions, and that was complicated, at least more so than what we've been doing. And now we see that the idea of arc length, sector area, degree measure, and the circular motion, very simple in the sense that they're very intuitive, at least in the way we think. So now we have a way to bridge degree measure, which is a human convention, with the pure measure, which exists in our universe. So again, here for degree measure, I have to admit that when I was in high school physics, degree measure was convenient. And of course, we'd get to math class and the professor would be, no, radian measure. So I've been there too. And of course, as you continue your work, depending on what field you actually enter, you may be more disposed to degree measures as an engineer. But of course, when you're doing your calculus calculations, you will definitely have to use your pure measure of the radians. So again, I will send out invitations for my office hours today. So have a good day and enjoy studying your pre-calculus. And I'll look forward to seeing you at our office hours. Bye. I got to let the bug man in.